All right. Welcome to the next video. So instead of moving right along to the next topic, I think we're having a little bit of trouble with these types of problems. So I wanted to spend a little bit more time talking specifically about some problem-solving strategies that you can use when you encounter a gas problem, okay, like an ideal gas problem. What I've done here is I've tried to sort of divide all of the problems that you might encounter up into one of two categories, okay? So I'm going to talk about these in turn, and then I'm going to do an example of each one. The first type is where you have static conditions. Static meaning unchanging, okay? So the conditions are sort of set and specified. Like it says here, these problems consist of a scenario where several parameters are given and you are often solving for one missing variable, okay? In these types of problems, more often than not, you're going to use the ideal gas law to solve for the missing variable. And then you just need to be careful making sure that your units are in sort of the standard form that they need to be in, right? Understanding what each of these variables represents. Your volume needs to be in liters, okay? Your pressure needs to be in either atmospheres or torr, because your R values, okay, the values for the gas constant, the only two values that you have access to, it's either in atmospheres or torr. So you need to use one of those pressures, right, in order to be able to use an appropriate R value. And then also you need to make sure that your temperature is in Kelvin, okay? So make sure that your units are in this form, or in one of these options here, atmosphere or torr. Choose the R value that matches those units, and these are relatively straightforward problems. Some things that might get a little bit spooky, okay, is this variable n, okay? N is moles, okay? If you're given grams, okay, you need to convert that to moles. If you're given number of particles, you need to convert that to moles. So this number of n, this value n here, that does need to be in units of moles as well. I'll add that into this slide here when I get done with the video. Okay, that's type 1, static conditions. Okay, type 2 is the opposite, right? Changing conditions. So these problems consist of scenario where the conditions are changing from one state to another, okay? Usually you're going to see words like, increasing the pressure or decreasing the volume or increasing the temperature, things like that. That's going to clue you into to realizing that, hey, this is going from one state to another. I have changing conditions. Usually what you're doing here is solving for one of the variables in one of the states, either the before or the after, usually the after, okay? What you're going to do here, and I'll go through the steps in more detail when I do the example, you're going to use the ideal gas law to identify which variables are held constant between the states. And you're going to use what you have there to set up a proportion to solve for the missing variable, okay? And once again, you do need to ensure that your units are in some sort of standard form, okay? Just like with type 1 problems, all right? So let's actually go do an example, okay, of each of these types. This is an example of a type 1 problem, static conditions, okay? This is from chapter 5, number 55. The steel reaction vessel of a bomb calorimeter, which has a volume of 75 milliliters, also known as 0.075 liters, okay? This reaction vessel is charged with oxygen gas up to a pressure of 14.5 atmospheres at 22 degrees C. Okay, and so these are the things that I would write down first when you get to this problem, right? You read this problem as you're reading it. Write these things down on your paper, right? These are your conditions, okay? And you can see there's nothing changing here, right? We're not going from one pressure to another, or from one temperature to another, or from one volume to another. We're just asked to calculate the moles of oxygen, okay? So N is our missing variable here. Okay. Now, let's take a look at my units. I have liters, atmospheres, degrees Celsius. Okay, so I need to convert this to Kelvin. Once again, if you have degrees Celsius, all you have to do is add 273. Okay, so this is going to be 295 Kelvin. Let me make sure that's right. Yeah. Okay, 295 Kelvin. All right. So your ideal gas law, PV is equal to nRT. We're solving for N. Okay. So before I plug things in, I'm going to go ahead and solve for N. Okay. So I'm going to divide both sides by RT. Okay. So N is equal to this, right? And I'll go ahead and write that out again. P times V over RT. Okay. Now we know most of these things. We have the pressure, we have the volume, and we have the temperature. What we don't have is R. And so that's where we need to use the reference sheet. Okay. Let me grab mine from over here. Okay. On the reference sheet, the gas constant for R, there's 3 numbers there. The first one we're not going to use for a little while. Okay, so that 8.314 joules per mole Kelvin, we're not going to be using that one until a little bit later in the course. The next 2, which actually have pressure units in them, either atmospheres or torr, those are the 2 R values that you're going to be using in these problems. The one that we want to use is the first, or well, I guess the second one, that has atmospheres in its units, because that's the unit that we have, right? So I'll just jot that down here. R is equal to 0.08206. And the units are liter atmospheres per mole Kelvin. Okay, so let me plug everything in here. 14.5 atmospheres for my pressure, 0.075 liters for my volume. This is my value of R here, 0.08206 liter atmospheres per mole Kelvin, and then my temperature, 295 Kelvin. Okay, and as you can see here, the units do all cancel out other than moles. Okay, we've got atmospheres in the numerator and then atmospheres in the numerator of the denominator, okay, which means it's in the denominator. Same thing with liters, okay, and then I've got Kelvin here and then Kelvin here, so denominator and then denominator of the denominator, which means it's actually in the numerator, and so everything cancels out except for moles, okay, and then I can grab my calculator here real quick and do this problem. 14.5 times 0.075 divided by 0.08206 and 295 divided by 295. Okay, so the value I get is 0.0449. Okay, it looks like they've given us 3 sig figs in a couple of different places, so I'm going to go with 3 sig figs here as well. And this is moles of O2, oxygen gas. Okay. If it asked for the grams, you could then take this mole value and multiply by the molar mass. You could get grams. If it asked for the number of particles, you could take this number here and multiply by Avogadro's number to figure out how many particles or how many molecules of O2. Okay. This is a static conditions type problem. Nothing is changing. They've just given you some of the parameters. You're solving for the missing one. Okay. All right. Let's clear this up. Go to the next problem. This is an example of a type 2 problem where we have changing conditions. Okay. I'm going to do the work down here. I'm going to write things up here. I'm going to write sort of my conditions on either side of this line. Okay. So I'm going to label this before and after. I guess I'm getting a little bit ahead of myself. How do I know that this is a changing conditions problem? Well, let's just read it. Okay, it says a sealed balloon is filled with 1 liter of helium at 23 degrees Celsius and 1 atmosphere. The balloon rises to a point in the atmosphere where the pressure is 220 torr and the temperature is negative 31 degrees C. What is the change in volume of the balloon as it ascends? Okay, so you see that? What is the change in volume? Okay, so that's a big clue. Another big clue, right, is that we've got 2 different temperatures, right? We have 2 different pressures, okay? So we're clearly encountering a change in conditions, okay? So this wants us to calculate what is the change in volume of the balloon as it ascends from 1 atmosphere to a pressure of 220 torr. So this balloon is starting at some altitude, it's rising to a point in the atmosphere, right, where it's at some new state, and we're going to be calculating the change in volume, okay? So let me write my before and after information. Okay, so before, I know that the volume, I'm going to label this V1 or V, you could say V1 or you could do V sub I, so V initial, either of those things is fine. This is 1 liter. My temperature is 23 degrees Celsius plus 273, that would be 296 Kelvin, okay? And then pressure is 1 atmosphere. Okay. All right. The balloon rises to a point, okay, where the pressure, okay, so my new pressure is 220 torr. Now you might be thinking, why are they doing this to us? Why are they giving us 2 different units? Okay. You are going to need to convert one of them to the other, okay? Doesn't really matter which way you do it, okay, but they are going to need to be the same unit. We'll get to that in a minute. The new temperature is negative 31 degrees C. I'll go ahead and do my calculator on this one. So negative 31 plus 273, 242 Kelvin. This is a good example of why you have to use Kelvin. You try to do a calculation like this with a negative temperature, you're going to get like a negative volume or something. Things don't work out. So that's why we have to use this, what is called an absolute temperature scale, okay, where absolute 0 is 0 Kelvin. All right, and then what we're needing to do here is solve for the new volume. Okay, and really we're going to be calculating the change in volume. So at the end of the day, we're going to be subtracting these volume values, but we do need to calculate this missing volume. Okay. All right, let me go ahead and convert my pressure. I believe the conversion factor is that 1 atmosphere is equal to 760 torr. So let me just convert this to atmospheres. If I do 220 torr times 1 atmosphere per 760 torr, so divide by 760, that's going to give me my atmosphere value. This is 0.289 atmospheres. Okay, so here's all of my information. Okay, and guys, I really would encourage you, okay, especially if you're struggling with these at all, to write things out like this. Okay, I know it seems like a lot of work, but you know what's more work? Staring at your page and not getting it done. Okay, so writing things out, making a table before, after, writing everything out with the units, okay, question marks for things that you don't know, that is going to help. Okay, your problem-solving strategy. What are you supposed to do? Okay, this is how I'm going to teach this to you. Each time you're doing a changing conditions problem, I want you to take the ideal gas law, write it out, and underline the variables that are going to be constant, okay, unchanging between your conditions. What is constant, okay, in this equation? Well, you can see here, your your volume, temperature, and pressure, those are changing, okay? So P, V, and T are changing. What's not changing is N, okay? It's a sealed balloon, okay? So particles are not escaping or entering into the balloon. The amount of matter inside of the balloon, the number of particles, the number of moles inside the balloon, that is constant between the two scenarios, or between the two conditions, okay, between the two states. Also, R is going to be constant, okay, because R is a constant. It's literally called a gas constant, okay? When you identify what variables are constant, lump them over to the same side. Okay, so N and R happen to be over on the same side. Everything else you want to have on the other side of the equation. Okay, what that means for us then is we're going to divide both sides of this equation by t. I don't want t over here with the constant stuff. I want some expression equal to a constant. Okay, and that's what this gives me. Okay, PV over T is equal to N times R. But for this scenario, N times R is a constant value. I don't know what it is, okay, but it's a constant value. What this allows you to do is set up a proportion, okay, because no matter what the pressure times the volume divided by the temperature is, for any state that this balloon might be in, it's going to be a constant value, okay? So the initial pressure times the initial volume divided by the initial temperature is going to be equal to the same thing for the second state. Okay, and if there was a third state, we could, this would be equal to P3 times V3 divided by T3. Okay, so what you can do then is plug in all of your values here. You have all of these things. You're only missing one value. Okay, so let's do it. P1, I'm not going to write my units here because I want to save my hand a little bit. It's kind of hard to write with the mouse on this thing. So this is 1 times 1 atmosphere times 1 liter, divided by 296. This is equal to my pressure, my new pressure, P2, 0.289 times V2, right? That's what I don't know, V2, divided by 242 Kelvin, okay? You can solve this however you want, okay? Some people might think that it's easier to cross multiply. Some people might want to multiply both sides by 242, divide both sides by 0.289. Doesn't matter, okay? That's actually probably what I would do, is I would multiply both sides by 0.289, multiply both sides by 242 over 0.289. Okay, you see how that cancels there. Multiply this side of the equation by that as well. 242 over 0.289. And so your V2 is going to be equal to this big jumble of stuff. Okay, so let me do that real quick. 242 divided by 0.289 as well as 296. Okay, 2.83 liters. Okay, so my balloon has expanded. Okay, the new volume is 2.83 liters. Now, be careful, okay? You've done 99% of the job here, okay? But the question is asking you, what is the change in volume? The change in volume, right? Delta V, okay? How much does the volume change? Well, that would be 1.83 liters, right? Or you could write this out in a sentence. You could say, the balloon expands by 1.83 liters to a total volume of 2.83 liters, something like that, okay? Just be a little bit careful. Make sure you're answering exactly what the question's asking for, okay? All right, hopefully this helps. I think I'm going to assign a few more problems. I might grab a few that are outside of the textbook. I just want us to have a little bit more practice with this, okay? I wasn't anticipating this to be quite as difficult as it's turning out to be, and maybe that's just because we didn't really get any experience with this last year, given NTI, or at least not a ton of experience with it. So I don't think it's going to hurt for us to take an extra day and try to soak this in a little bit more, because it is important, and you definitely need to know how to solve these types of problems. Okay? All right, thanks for watching. See you in class next time.